Hi, everyone. So today we're going to talk about conservation of energy. And we start off with these two images. We have this one over here. This is a system boundary. This is an illustration of conservation of energy, right? The change in total amount of energy in the system is equal to the total amount of energy that crosses the boundary of the system, right? So you start with this initial amount of energy, and the change in total amount of energy has to do with any work done, heat added or lost, any waves, radiation, electrical transmission, or any matter that's going into or out of this set initial energy of kinetic, potential, and internal energies. Internal energies is like the internal temperature of an object or things like that. So what we're really only going to talk about in this class is work, adding energy or taking energy out of a system. Okay, we're not going to talk about heat, waves, E&M radiation, electrical transmission, or really any matter transfer, but we will talk about work, taking things out of a system. So let's look at this marble. Okay, it says, explain the conservation of energy I might use for the marble on the ramp. Okay, the COE. So the COE for this, right? Let's say the marble travels from point B to point A. Okay, so we could say that it has potential energy of gravity at point B plus any kinetic energy it has at point B would equal the potential energy of gravity it has at point A plus any kinetic energy it has at point A plus any work done by friction on the way down. So that's the conservation of energy we could deal with. Now, if we want to expand that, right, we have our mgh plus 1/2 mvb squared equals mgh final, let's say that's h naught, plus 1/2 mva squared plus the work done by friction, which is mu nd. Now, the normal force, since this is a constant path right here that we have, and it's at a constant angle theta, we'd be able to find the normal force just by doing the usual free body diagram information. But if it's a curvy path, that's going to be really complicated. Now, this can get even further expanded, right? If we had a second object, we could also say that this is equal to the potential energy at point C plus kinetic energy at point C plus any work of friction done between those 2 points. So then we can also expand this as, that would still be mgh final plus 1/2 mvc squared plus mu ndc compared to mu nda, the distance traveled to get to C versus the distance traveled to get to A. I guess the normal force at A and C would also be different. So we can expand this to get much, much bigger. Then if we had a second object in the system, then that would expand it even larger, right? So COE can get expanded quite large, but you also have to look, all of these variables are not very complex variables. So don't let the length of the problem get you down. All right, now, converting potential energy into kinetic. Okay, this is kind of the whole point of conservation of energy, right? You start with potential energy, and it can get converted into kinetic, or kinetic energy can get converted into potential energy. Now, that's how energy is conserved, right? The conservation of energy is that energy cannot be created or destroyed, but it does change forms, right? In this class, we are limited to what we're going to talk about form changing, right? We're just going to talk about mostly mechanical energy and friction. So here, we're just going to talk about potential energy converting into kinetic. So we have this ball of mass m at height h above the ground with an initial speed v naught. Determine the speed of the ball at height y above the ground and start by setting up the conservation of energy. So when we start the conservation of energy, right, or COE, okay, we would say we have initial potential gravity, initial kinetic energy, that equals the final gravitational potential energy plus the final kinetic energy. We're not going to calculate any drag resistance here. We don't have the equation for that. We're assuming there's no drag. And there's no friction. There's no springs involved. So we'll stick with this. Okay. Now, if we want to find the velocity, right? Yeah, we want to find the speed of the ball. So what we will do is we will, first, let's decide what we want to do for our ZPL. We can set our ZPL in two different places. We could set it at Y, or we could set it at the ground, okay? So if we, let's say we start at the ground, right? Our Y naught, right, is H. And our Y final is Y. But if we set our ZPL at Y, then our initial height here, right, our Y initial would be H minus Y, and then our Y final would be 0, right? So it depends on which one you want to do, okay? If you choose your ZPL to be Y, then that means that your gravitational potential final is going to be 0. If you choose your ZPL to be the ground, you still have to do both, but you don't have to do the math in the H minus Y, right? So, but I mean, it's going to trade off. So it's really up to you what you feel most comfortable with. I'm going to choose the ground just so we can do the demonstration of converting the potential energy. Don't want to eliminate too much for the example. So we have here mgh, right? Because we had these initial and final values, plus 1/2 mv naught squared equals mgy plus 1/2 mv final squared. So this is what we start with. Okay. What I'll do first is I will move our. I'm gonna do a demonstration real quick. Okay. So if we move mgh and we're gonna subtract mgy, that would equal 1/2 mv final squared minus 1/2 mv naught squared. Okay. Notice that this final minus initial is delta K. Notice that this is initial minus final, that is negative UG. Okay. Notice that the change in energy in the potential, okay, is the same magnitude but opposite in sign as the change in kinetic, which means that you're going to lose potential energy and gain kinetic, right? So that's the demonstration I wanted to show you there, is that we are just showing mathematically we are changing our gravitational potential by losing it, and we're increasing by the exact same amount. So anyway, it asked for the speed of the ball at height y, so that's our v final. Let's solve for v final. So we'll multiply by 2 to get those 1/2 out of the way. So we have 2 mg. I'm going to factor that out. Notice that this h minus y, it shows up anyway. Even more proof than that. It's just kind of arbitrary. And that will equal m times v final squared minus v naught squared. Those m's can cancel right out of there. So if we're solving for v final squared, we have 2g times h minus y plus v naught squared, all under a square root, equals v final. Okay. Now, I do want to show you again one more example. If you are familiar with the kinematic equations, you know that v final squared equals v naught squared plus 2a delta x. Okay. Well, let's say that this is delta y because we're only traveling in the y direction, right? Well, if we want to solve for v final, notice that v final equals the square root of 2a delta y plus v naught squared. Do you see the resemblance between these two? If g equals a, and H minus Y equals delta Y, then it's basically the same equation, right? We are doing the same thing that the third orange could do, or the third kinematic equation. The only difference is we used conservation of energy to arrive at that. All right. Now, that is our answer for now. We don't have any values for those variables, so that's our answer, right? Our answer is the third orange. Okay. And now remember, this has no non-conservative forces. If there's non-conservative forces, general kinematics wouldn't apply. This is also a very simple general kinematics question that we would have gone over in chapters like 2 or 3 or 4 or something like that. So this is just a new way to approach that idea. Right? So what if we have two objects with potential energy or kinetic energy? Now, we have two masses connected by a light string and a frictionless pulley. So do both masses have to have the same ZPL? No, they don't have to have the same ZPL. Now, if we look here, okay, it probably makes sense because M2 sits on a table and we're actually finding the speed when M1 hits the table, right? So this is actually where M1 will have its final resting place. So it makes sense to put your ZPL right there at the table. However, sometimes that's not always the most simple scenario. Okay, so they don't have to. However, in this example, it is what we're going to do because it's going to make our problem easier. Now, use a COE to find the speed when M1 hits the table. So let's look at all of our energies, right? Let's get a COE. Okay. So the initial energy. Okay, you've got you've got UG1 naught plus UG2 naught plus K1 naught plus K2 naught equals UG1 final plus UG2 final plus K1 final plus K2 final. No friction, no springs, so we're going to end it there. Now, obviously, some of these are going to cancel, right? For example, if we set our ZPL at the table, right, that is the initial value for 2. That is the final value for 1. We are going to assume that they start at rest. Okay? If M2 is sitting on the table, we can say that those are both at rest. Okay? So what we're going to result is that 1 has potential energy, and that is going to give 2 potential energy by raising it off the table, and they will both start moving. Okay? So this is also interesting to look at there. The only thing that starts out with energy is the first mass, right? But then all of that energy gets turned into these other masses as it travels to the table. Now let's find this speed. Okay, we are looking for V1 final. Okay, so let's find it. Let's expand that out. We have M1 GH. Let's see. Yeah, M1 has a starting height of H. Good. That equals M2GH. It's going to travel the exact same height, right? So then we have 1/2 M1 V final 1 squared plus 1/2 M2 V final of 2 squared. Now, we do know one thing about these pulleys, right? Pulleys, the objects on each end of the pulley has to move at the same rate, assuming this is just a simple pulley. If it moves slower than the other object, then your string breaks, right? It's going to start stretching and it breaks. If one object moves faster than the other, then you're going to have slack in your pulley, and then the string could just fall off the pulley in general. So we can say that VF1 equals VF2, and we'll get rid of the 1 and 2. Now it's just V final. Okay? that is going to be key in making this problem work. Now let's see what we can do. We can factor out a GH. So we've got GH, and we'll subtract M2 over. So you've got M1 minus M2. Okay, I just subtracted that guy over. That's going to equal 1/2 V final squared times M1 plus M2. Now let's multiply by 2. 2GH M1 minus M2, and we'll divide by M1 plus M2, and we'll put that all under a square root to get V final. Okay, so that is the difference between finding V final for one object and V final for another. Notice that, let's see if I can find it. Where are we at? This right here, a V final for one object, right? Just the square root of 2a delta x plus the initial velocity if it had any. Here, a little bit more complicated, right? So when there is more than one object, then you can't simplify nearly as much. First, because you've got more than one mass, right? M1 and M2 are all over the place. And if we had a V naught, then that would change things up as well. Luckily here, we started at rest. But that is what we arrive at. That is how you find the speed when M1 hits the table in a situation with two masses connected to a frictionless light pulley connected by a light string. Now let's talk about friction and mechanical energy. Okay. So friction and mechanical energy. First, what is mechanical energy in physics? So mechanical energy, okay, mechanical energy, this is the sum of all potential and kinetic energies. So potential and kinetic energies. So if you have more than one potential, like potential gravity, potential in a spring, and then all of the kinetic energies of moving objects, all of that summed up is the mechanical energy of a system. Now, in cases with friction, is the mechanical energy of the object conserved? If this is just one object moving and there is friction, then no, right? Let's say we have UG naught plus K naught equals UGF plus KF. If that was the case, then you would say, yes, these are conserved. But then if you have the work of friction taking energy out, these, right, the mechanical energies are no longer conserved. Okay? But the overall energy, the overall energy would be conserved. So these would equal each other. But if you cut off the work of friction and try to say, is the mechanical energy conserved? Are all the potential and kinetic energies conserved? No, they're not. If there's a non-conservative force involved, then they're not conserved. But we can see that all of the overall energy is conserved because we can actually calculate how much work is lost due to friction. So to prove that we can actually do this, let's do it. For example, we have a 20-kilogram child at rest, like in the picture below or over here, right? We've got a 20-kilogram child at rest, rides down a slide of height 5 meters. How much mechanical energy is lost to friction if VF equals 3 meters per second? So let's get a COE. We actually have our COE right here, right? This is the COE that we will use. We've got our potential energies and our final energies. Now, let's see, what should we use for our ZPL? I would say bottom of the slide, right? That would be our ZPL. The child starts at rest. So what we are left with is UG naught equals KF plus work of friction, right? All of the potential energy goes into the motion of the child as it reaches the bottom, and some energy is lost due to friction. So let's see how much is actually lost due to friction. So we have mgh equals 1/2 mv final squared plus work done by friction. So let's subtract that over. You have mgh minus 1/2 mv final squared equals your work done by friction. Let's see, what are our givens? We have m equals 20 kilograms, h is 5 meters, v final is 3 meters per second. We already mentioned v naught is 0. We have everything we need, so let's plug this in. I'll actually make this more simple. I'll do m times gh minus 1/2 v final squared equals work of friction. Simplify that a little bit. So we've got 20 times 9.81 times 5 minus 1/2. V final is 3, but it's squared. And what you get is 891 joules. So we can calculate how much work friction was doing against the child, right? It's taking out 891 joules of energy as the child goes down the slide. So that is how we're going to do our conservation of energy problems. Now, as we go, we're going to do more and more complex conservation of energy problems. This is just the start, looking at mechanical energy and how friction can take away some of that mechanical energy.